Alright, hello everyone and welcome back to another video. Today we're going over the problem longest consecutive sequence from week 1 of the June Leak Coding Challenge. So this problem has a fairly simple setup. There's an array of numbers and you have to return the length of the longest consecutive sequence. So a consecutive sequence just consists of numbers that are like right next to each other in terms of like their size. So 1, 2, 3, 4 would be a consecutive sequence with a length of 4. And yeah, so you can notice that the numbers can be placed in any order in the array. They just have to be in the array. And while it would be extremely convenient to just be able to run a sort and then go through the array, because then all the numbers will be consecutive anyway, so you just have to check if they're all differ by 1 to make them a sequence. But because we have to write an algorithm that runs in O of n time, and to sort this it would take n log n time, the sorting is out of the window, which makes this a bit more challenging. And so if we look at their next test case, it's just easy to see there's also has a chance of duplicate numbers, which doesn't really matter for the solution we're gonna go over, but the numbers would go from 0 to 8, and each number would be in the range of negative 10 to the 9 and 10 to the 9. This is actually a semi-important constraint, because without it, one strategy we might want to try, let's just say all the numbers were in the range, like nums I was also in the range 0 to 10 to the 5, we could simply keep like a Boolean array, and whenever we run into a number, we just set that index of the array to true, and we find the longest consecutive like series of trues inside of our Boolean array. But because these numbers are so large, that strategy is also out of the window. So we know that we must write an algorithm in O of n time, and we can't really depend on just allocating a ton of memory to make it work. So now I'll go over the solution that I came up with. So while it may not be readily apparent that we can use disjoint sets to solve this problem, disjoint sets are actually a really convenient way to solve this problem, because of it lends itself to this problem really well. So I'll explain what I mean by that. So if we have our array of numbers, like let's just say all our numbers are in this array, what's their test case, like 4, 1, 3, 2. So we're supposed to detect that this is like a consecutive sequence. So what we can do is, whenever we run across a new number in the array, we can initialize it to its own disjoint set. Then when we run into another one, we can add it to its own as well, and we check if we should union it with any other sets. Because the only other set in here is 4, we can't union it with anything, because we can only union it with a consecutive element. It's like 3 or 2. And then at the end of this like process, we should be able to, if we union it correctly, the size of every set inside of our disjoint set will represent how long that sequence is. So we look at the next number, 3. That's a new number. So we can initialize it to its own set, right? But because we know that 4 is in the set and 4 is like consecutive with 3, we want to union 3 and 4. So we can union these into one set. So we can simply put 3 and 4 into one set here, and that'll be the set. So that's how we would process 3. And now we would process 2. So we'd initialize 2 as its own set, and then check if we have 3 in a set. So we know that we have 3, and because 3 is adjacent to 2, we would find the set of 3, which is this set here, and union 2 into it. So we would add 2 into it, and we would also check the other adjacent number to 2, which is 1. And we can find this set of 1 and union it together as well. So at the end, we should be able to find this group of 1, 2, 3, and 4 in one set in our disjoint sets. And of course, if we have a different number here, like 100, when we add 100, we'll check if we have a 99 or a 101. Because there are no groups with that, 100 will just stay as its own group. But if we had like another group 99, when we add it in, we want to check if we should union it with 100. So basically, by keeping these disjoint sets, and whenever you add a number into this disjoint set, you should check if you should union that number, the set containing the number right under it, and the set containing the number right above it. So yeah, so for example, when I added 2, I want to check if 3 belongs in a set. So if I know that 3 belongs in this set, I should union these two sets, the set I just made with 2 and the set that contains 3. And then after that, I'll check if there's a set called with if there's a set with 1. If there's a set with 1, this can also have like 0, 1, whatever. All the other elements in this set, when we union it, then all these set elements in this set will go into this set. So then we'll have one big set with like 0, 1, whatever was in this set, whatever was in this set, and our new set of 2, because we'll union all those sets together. And disjoint sets are really useful for this because unioning sets together is very quick. It's nearly constant time if you implement a disjoint set with path compression and union by weight. So if you guys don't know about that, I will just type it out here in case you want to search it up. So path compression union by weight. And what these two things do is they allow us to basically find these sets and union them together, like combining them, in nearly constant time, which is incredibly important for our purpose in this problem, because we want our algorithm to run in O of n time. So if we need to check every element in our array once, all the operations we do with it have to be pretty much constant time. And disjoint sets will be really useful because they will let us kind of achieve that constant time. Because for every element, we just need to check if we just need to add its set and then check if we need to union it with a set that contains 1 and a set that contains 3. And since unioning these sets using a disjoint set is constant time, that allows us to run in O of n time. So it's technically a little bit slower than constant time, but it's good enough for the purpose of the problem, and it still will be much faster than a n log n sorting approach. So yeah, so that's the general idea. And after we add and process each of these numbers in the array by making it set and then unioning it with the set that contains the number below it and above it, then we will end up with a bunch of these sets, right? And we just need to find the largest set and return that. So if this set has like 4 elements, this set has 2, and this set has 1, we know the longest consecutive sequence will be 4 because this set has 4 elements in it, right? So now that we know the basic idea of how this works, let's get into how to implement this. So this is just a fairly standard disjoint set implementation. So we will represent this sort of tree structure as like, well, not this tree structure, but like this kind of grouping structure using like a list, which is basically going to function similar to an array, but a list is just more convenient for our purposes. And we'll maintain a map to keep track of um, all the values we have in our disjoint set and where they are stored in our list of pointers. So let me just delete this real quick. So what we're essentially implementing is we're going to have a list, right? And we're going to have a map that tells us where elements belong inside the list. So if we have, like, if we want to add the number 3, like we run across the number 3 in our array, we will add that to the next available spot in our list. Let's just say it's this spot here. We'll add that to our list. Then we'll have a map saying, add an entry in our map saying with the key of 3 and the value of 1, because we know the number 3 is at index 1 of this array. And so then we won't actually add 3 here. We won't actually add 3 up here. We will just add a -1, because in disjoint sets that will represent the size of the current set, and it's negative because that means it's like the representative of the set. And so we'll have a map saying that element 3 is at index 1 of our list, and this negative number will signify that this is the representative of a set and that there are 1 elements inside of the set. So then let's say we want to add an element of 4. That's like the next number in the array. Then what we'll do is we will first add that to the next thing. So we'll initialize 4 to be its own set inside of our disjoint set. So it kind of look like this. We'll add 4 and we'll say that belongs at index 2. And then we'll check if we need to union. Because our map has a key of 3, we know that one set in this has 3. So we can get the set of 3, that's 1. So we know that this index is at 1. So then what we can do is we can change this index, this value here, to be 1. So now when we want to find the set of 4, we can simply, and when we union them, we'll also change this to 2, right? Because now 4 will belong to the group of 3. So what we can do is we can change these two numbers by simply adding them together for this 3. So this will symbolize -2, and this means that 4 belongs in the group that is the representative of the group is at index 1. So now when I want to find the group 4 belongs in, I look at index 2. This tells me that this is not the representative of a group. So I look at index 1 to find the representative of the group, and I see -2. That means there are 2 elements in this set right now. Because we union them together, we have 3 and 4. And I mean, I'm not going to go over the entire implementation of how to implement a disjoint set, but that's essentially what we're doing with a few more things like path compression and union by weight. But I won't go into that now. So the important thing is just to know for this problem, when we're implementing this disjoint set, we will keep track of our groups like that by having like a sort of pointer system. So regularly, these are just empty like sets with like 3 and 4, and when we union them together, we essentially connect them by using like a pointer. And then if we have like another, if we want to add 2, we can add 2 as its own set, and then we know 3 is in our disjoint set, so we can connect them together. And then when we look at 2, we can find that as representative is 3, and we know 3 is connected to these however many things it's connected to, and that'll say the size of the consecutive sequence. So that's essentially what we do here. So when we add a number, so first let's go over the actual code inside of the method. So we will initialize a new disjoint set of this class. I'll explain how this class is implemented later, but for now, just think about it as maintaining these sets, right? So then for every number inside of our array, we'll just add that. And when we add it inside of this, we'll check if we can union it with a set that is one number less, right? So if we add 2 into our disjoint set, and the disjoint set already has a set with 3 and maybe some other numbers, it doesn't matter. When we add 2, we want to check if we can union it with 1. In this case, 1 doesn't exist, so it's not there. But if we have a set of 3, we want to union them together. So yeah, so for every number inside of our array, we'll add that to our disjoint set, and when we add it, we want to check if we can union it with the set of a number just below or above it. And here is essentially our what we talked about earlier. We will have index of, which represents where that element is stored, and then we will put a -1 in place in that array to symbolize that it is the representative of its own set, and then we will see if we can union it with another set. And when we union it with another set, we will just find the representative of each set, and then we union them by pointing one representative to the other. So in that case, this is what it does. So find set will just return the index of the representative that A belongs to. So if A is a representative of its own group, it'll just return the index of A. Otherwise, it'll do this sort of hopping system, and it'll eventually come up to the index of 1. So because this tells it to go to index 1, right? So then it will find that the representative of the group of A is at index 1. So now that we have these two representatives, so let's just say we have a disjoint set with some random things, and then we have another disjoint set with some random things here. Let's just say, oh, we found the representative, that's this guy, and this guy's representative. We can just add these representatives together, and that'll create a link between this entire set. So that's essentially what we're doing here. We're setting one representative to point to the other, and then this other one we point to, that'll store the new value of how many items are in the set. So we get the value at the index of the first representative, then we get the index of the value at the second representative. So there will be negative numbers. So the representative will have, like, let's just say -3. That means there are 3 elements inside of this representative's like group, and then let's just say the other one's -4. When we union them, we want this one to point to the index of this one, and this one to have a value of -7, because now we know that this guy also holds these guys that are in whatever here, right? So that's what we do. So we add these two negative numbers together to get the total number of elements inside of that group. Then we just union them together by pointing one to the other and setting that one to be the total number of elements. So, and this if else just implements the union by weight, because when we union things together, we want the set with less elements to go under the set with more elements. And a quick explanation why is because, let's say this one only has 2 elements, but this one has like a lot of elements, like all over the place. If we point this one to this representative, we'll have like a lot of random stuff down here, and that makes it harder to find the set because we'll have to travel through a lot of these jumps in our array, because we'll start at an index and we'll kind of jump until we find the index of its representative, right? But if we put this one under the tall one, this node will have a lot of whatever, and this short one, it'll only add a little bit. So you only need to perform 2 jumps. And if we put this one under that one, you have to do more jumps. So the more jumps you need to do, it kind of ruins the constant time that we need. So that's why we want to use that. And the find set implements path compression. So basically what this does is that this also helps us achieve constant time like unions, because when we union, we define these sets, right? So if we constantly have to if we have like constant sets here and we constantly have to perform like 2 jumps, 3 jumps, that's really bad, right? To get to the representative of the set. Instead, what we can do is, if we keep track of all the things we jump to and we know that they end up here, we can just point all of these to jump directly to the one we ended up at. So then afterwards, whenever we want to find the set of these, it'll look more like this, where you can jump directly to its representative, because we essentially compressed the path. Because we did all these jumps, we realized that all of them lead to this representative, then we can just make them all jump directly there. So we do that just by remembering all the indexes that we had to jump to, and then we move our index to the thing that we want to go, the new index that we want to go to, and then at the end we'll just set all of the indexes that we traveled across to the ending index that we ended at, and we'll return the index that we ended at as the index of the representative of our set. And then yeah, so then the only other modification is that you need a method for the largest set, and because in our list we will have negative numbers representing the head of a set, and however much that number is how many elements it has, right? So we can just go through and find the like the most negative number, and that represents, like, if we have a set with -5 in it and a set with like -9, we'll know that this set contains 9 elements and this set only contains 5 elements. So we'll know that the longest consecutive elements are 9. So if for every number we have, if it is less than the maximum, then we set the maximum to that number, and we'll return the absolute value of that. So this will just return the largest set that we currently have in our disjoint sets. So yeah, and that way we can just return disjoint the largest set, which will represent the longest consecutive series of numbers that are present in the array. And so let's run this, and a runtime analysis is kind of pointless in this one, except because we already know that we have to run an algorithm in O of n time, and this would run in O of n time, because when we initialize a disjoint set, and we are only looping through the array of numbers once, because in our for loop we don't have any nesting, so this for loop will run n times, and inside the for loop, adding to a disjoint set and unioning sets together in a disjoint set are both should both be pretty much constant time operations. So this outer for loop will run n times, and inside of it it'll just be a constant time operation, so it's like n times a constant. So the overall runtime of this method will be O of n. And yeah, so that's about it for this problem. I hope you guys enjoyed the video, and I'll see you guys later. Thank you very much for watching.